Hi, everyone. I'm Javier Garcia. I think I'm supposed to start with introduction. Is that right, Sasha?
Yes, that's correct.
Okay. I can either share my screen or or you guys are gonna show the slides.
Well, the slides are uploaded, so it was there just a second ago, but you can also share the screen, it's fine.
Actually, that will be better for me because I can update the figure, one of the figures that we had to someone slightly better. So let me do that. Do you see my screen right now?
Yes, it's clearly seen.
Okay, great. So this is a large topic, and we were afraid that we might not have time to cover everything in detail. So we kind of narrow it down to at least a couple of important questions. One has to do with the truncation of the disk, and the other one with the disk jet and corona connection. So I'll give a very brief introduction on the discussion of the truncation of the accretion disk. And I apologize for taking everything from my own papers, but it was easier for me to show the main point here, which is there is a lot of discussion in the current literature about how truncated accretion disk is specifically in the higher state. I think a lot of the discussion has been concentrated in the case of GX339-4, because it's a very well studied source, and there's plenty of data for it. But it's not unique to this one. There are similar claims or disputes in other sources like Maxit 1820 and so forth. So the question, I think the important question here is to understand not whether this is truncated or not, is about more of the details, how truncated it is and when through the outbursts. Because sometimes I find it a little bit confusing when there are discussions referring to whether the disk is truncated or not, but there is no specification on what do people really mean when it's truncated, for example, in the higher state. As you can see in the figure here on the right, the typical hardness intensity diagram made with RXT data for GX339 show that the higher state obviously covers quite a range in luminosity, probably a factor of 20. And what we've done in the past is look at this data with a lot of care in these boxes defined here, and applying reflection spectroscopy, we measure the evolution of the accretion disk. It is shown in the red points on the left as a function of luminosity. When comparing this with other values this is all reflection spectroscopy done with from different authors and different instruments. What we mainly see is there appear to be two possible solutions, so two claims. One that seems to, both of them show evolution of the inner edge of the accretion disk moving inwards as the luminosity increases. But there is a group of reported values that are clearly much more higher than the other ones. So what we found with reflection spectroscopy in this case is that the disk seems to be moving closer to the ISCO, which is shown in the dashed line here, as the source evolves towards the most luminous part of the higher state. However, at the same levels of luminosity, there are claims that have shown much larger truncation radius. So the big question here is to understand what is happening here, why some measurements are so different if they're all coming from similar techniques. So I could talk a lot more about this, but I would rather hear from the audience on this particular issue. When do you think the accretion disk should be truncated, and what kind of observations can we do to figure out this discrepancy?
So if I just add a couple of words here. So starting from the morning today, this question have been raised up a couple of times, maybe actually more than a couple of times. So this puts it very timely also. And then a few different aspects of this question. So it was put in a context on the different modeling And this kind of geometry, every time we do spectral modeling, we do timing modeling, actually we assume certain type of geometry. So this is rather important also to converge on this kind of topic. Maybe not today to converge, but at least to emphasize what we can do to make it closer, this estimate. So here it's like more than an order of magnitude difference in the Rin. So maybe we can do something to get them closer. So maybe we can start with the audience. Does anyone want to first tell us? Yes, Nick, please.
I want to mention I have any issues with my Slack at the moment, so I cannot see if people are writing there. If somebody else can let me know if something is happening in Slack, please.
A quick clarifying question. Is it the same data that the two papers have analyzed, the blue and the red,
it's
green?
It's the same source,
set of data for the same source?
It's the same source, different times, different instruments. So colors are, the colors are trying to highlight the fact that, for example, red is the RXT PCA, orange is NuStar, green is Swift XRT, dark green is Suzaku, and all the blue points are XMM, but XMM in timing mode. So I think that might be connected a little bit with that, with the fact that timing mode is a different sort of situation. There is also XMM not timing mode, so that done with the mouse that shows lower values down here.
Another simple question. Can the two groups of people try to analyze the same data so that we know what one does and what the other does on the same data? Then either they agree or they disagree. And if they disagree, then we should know why they disagree.
This has been done recently for one source, Maxi J1752. We published one observation in the hardest day. And I think, Andre, you might want to talk about your work on that. What I can say is Andre has shown that if you explain the continuum with a more of a hybrid quantization medium, so it has two different temperatures, so you have two contributions to the power law, the truncation radius goes to much higher values. However, I do have my personal criticisms to this work because they only analyze a very narrow band in energy. So I can't remember, Andre, are you the lead author on this paper or somebody else was?
Would you like to say?
For which, Tommaso, for which object you mean 18J 1820?
1752. J1752.
Oh, J1752, yeah. So we analyzed the same data and got different answers, but also for Maxi J1820, we did analyze the same data as in the paper by Bosson et al., in which they had lamppost and model, and we used, in one case, we used the same model, and we found that the high-square space has two minima, one corresponding to no truncation, but the inclination of the source of 30 degrees, another one truncated and inclination of 60-70 degrees. But all the data for that source show that both jet and the binary have inclination in the 60 to 70 range, and 30 degrees simply ruled out. And then in the same paper, we also analyzed more complex models and found that the best fit to the data with truncated disks.
So, right.
But
so
I think this issue of inclination is very major one, that we simply cannot have reflection models for Maxi J1820 at inclination 30 degrees. They disagree with other constraints.
Right. So I think the problem that I see with these comparisons is that even if we're using the same technique, everything is quite model dependent. Depends on what you assume for your continuum. And in the case of Maxi J1820, it happens to be such a beautiful, rich data that the standard reflection modeling doesn't work. You need to you're left with residuals that require adding additional components, and your assumptions on whether, in the case of Buisson paper, we assume 2 lampposts illuminating the disk. Andre is moving towards having 2 different quantization mediums that change the way the continuum looks like, and that will affect the shape of the iron line and all the reflection features that you observe. So I think a question that we probably won't be able to answer here, but a question I want to leave to the audience is to think about what sort of observations we can do to kind of walk away from this strong model dependence and figure out what's happening with the truncation level of the accretion disk.
So we have another
Victoria?
question or comment in the audience.
Okay.
Barbara, please.
Hi, it's Barbara De Marco. I had a comment about the continuum. It's not, well, it's true that we assume that, but it's supported by spectral timing results. They were shown by Geron, like on MaxiJ 1820. They show that if you do RMS variability studies, the continuum looks like spectrally stratified. So when we fit this model to time average, well, when we fit time average models, we make an assumption, but it's supported by other results. What do you think about it?
Well, I think the idea of having a corona that is at a single temperature and only those, the standard thermal quantization is a little bit too naive and too limited. So I'm not surprised that the situation is more complicated. The part that confuses me is that we have looked at the shape of the iron line in a few cases, comparing the soft state with the hard state. And in general, the shape of the iron line and the reflection features tend to look quite similar, indicating that there is little evolution between, let me be specific, between the most luminous parts of the soft state and the hard state, and even throughout the transition. So I think it will be too much of a coincidence that in the hard state, you have a perfect arrangement of components that make the reflection features to look very similar to the ones in the soft state when you don't have that coronal emission anymore. And I think we all agree that the accretion disk is at the ISCO by the time the source is in the soft state. So I think that's the one thing that we sort of need to think a little bit more about. And Victoria has her hand raised for like a long time.
So I wanted to kind of like piggyback on the fact that inclination was mentioned a few times, and I guess this may be actually a question for Sasha, because I've seen in the recent day this paper on the extreme misalignment on Maxi 1820, which I haven't read, to admit. I just didn't have the time because I was co-organizing this meeting. So I guess my question is whether this strong misalignment may be a part of the explanation, and whether the strong misalignment would have also implication of this disk measurement, also because Andre mentioned explicitly, if I'm not confused, Maxi 1820. Sasha, do you feel free to take over and say something?
Yes, so just a small comment. I mean, this agreement is in between the data and the same data for different sources. So we also have the same disagreement for GX339 - 4. Either we need to assume that we all have, for all the black holes, we have the misalignment, and that causes these parts, these two alternative interpretations. But also I would like to mention that the estimates for the inner radius for the disk truncation scenario, they are quite high, so you wouldn't be able to explain it with misalignment if you just have, for example, misaligned or like retrograde black hole with the ISCO further away. So this should be something more than this misalignment.
Thank you.
So are there any other questions or comments? Yes, Vlodek has one.
What a Kruzak. In the spirit of bringing theory and observations together, I have to confess I am terribly puzzled today. We've seen many cartoons of accretion disks, and I do not know of a single physical model that corresponds to any of those cartoons. That's my statement number one. Statement number two is that in the past 5 years, there have been several radiative, relativistic MHD simulations of accretion disks. There's Ken Osuga's group in Japan, Jim Stone's group in Princeton. There's Chris Fragile in Carolina. And then there's the Coral Code group in Warsaw and Opava. And they make specific predictions for how disks, accretion disks look. And they look nothing like the cartoons that I've seen today. So I would encourage studies of reflection, etc. If you can get, without any a priori assumptions about the shape of the disk, if you can tell us what the geometry is without assuming anything. But if you're going to assume something, why not assume a physical model? Thank you.
Thanks, Wojtek. So now Agata would like to continue with that.
Here is Agata Różańska. I have a comment to your comment, because for instance, I miss a paper when people compare really simulations to each other between groups, because it's really hard to find, for instance, what is the density in those disks. I was trying a couple of times and it was really hard.
Can I say something? The topic of MHD simulations is quite broad, and until perhaps now it's changing a little bit, but for a long time there were not simulations for thin disks, which is really what we're talking about here. Most of the simulations in the past couple of decades have been, puffy disks, many cases non-rotating black holes, so they don't quite fit the bill for the sort of observations that we're trying to explain right up here. So whenever we're talking about reflection, the requirement is a little bit to have a proper, let's call it alpha disk, a thin accretion disk that is optically thick and have the right properties to produce strong reflection features. If you have something more like an ADAF or YF or whatever acronym people are using nowadays, it's going to be hard to see any reflection from that sort of outflow, accretion flow.
So we have a couple of more questions in the audience. Are there any in the chat?
Hi, this is Andrzej again. I have two clarifications. One, answering the comment by Victoria. What we know for March CJ 1820, we know the viewing angle of the jet is about 64 degrees, and the viewing angle of the binary of the normal to the plane is between 66 and 80. And the fact that there is extreme misalignment, this misalignment is in the actual system. It's not this misalignment, the statement that the misalignment is more by 40 degrees does not falsify the statement that one angle is 64 and another is 66. They could be both, but those are viewing angles. And this simply means that in the actual system, we have different axes of binary and the jet, and they are misaligned, but both happen to be projected to be seen with the same viewing angle. So the misalignment does not falsify the issue of reflection. And I think that what we did in our paper was taking the same model as Busson's model. In fact, we worked with him together on that issue. We took the same model and we found that there are two high square minima, one for 30 degrees and no truncation, another one was for 60, 70 degrees and high truncation. And in both cases, we took the double Lampos model, the same as Javier mentioned. So it's not that we took a different model with two comptinizations. Two comptinizations were introduced later in the paper, but as a basic test, we just found that the model with no truncation is in conflict with the measurement of inclination. Thank you.
Thank you, Andrew.
Yeah, that's a good
I-
point, but it still wouldn't necessarily. Sorry, just want to say that it wouldn't explain the discrepancy in GX 339 where we don't have strong evidence for warp this.
Okay, hi, this is Thomas Stauser. I have a comment on like the thin accretion disk, also regarding the GRMSD simulations. So one thing I think that is a little bit overlooked is that the relativistic reflection we were talking about here is coming really just from a more or less ring of a few RG, if you're looking in the extreme cases we're talking about here often. So it's not like the whole disk has to be thin. It's like it can be from 1.2 to maybe 5 RG that's producing like 90% of the reflection we're seeing. So we don't really need these huge thin disks you might imagine. A small, maybe thinner disk in the inner region would be enough here. Yes.
Or also to add my cent of advice, what you could also have is that you have just cold patches of gas near the midplane that fall in.
Okay, so we have another.
Some simulations now.
So are you suggesting that it could be a not? It could be you could have the situation of a non-thin disk of a
Kind
more
of a truncated disk with not really a thin disk, but sometimes that from the thin disk through the magnetospheric barrier, like in a magnetically arrested disk, like a cold patch of gas, like falls in, but it's not really a disk. It's more like an orbiting, how would you say it, orbiting segment of a thin disk or orbiting cold spot or whatever you want to call it.
I see. It will be interesting to see what's the time, the lifetime of those cold spots that coming from the simulations.
Yeah,
and whether they agree with the evolution that we see, because you can see where we measure reflection. At least in this case, we can see a nice evolution of the inner disk moving inwards.
Yeah.
Mm-hmm.
Okay, we have one
Sasha?
more question.
Yeah.
Actually, yes, it's Pierre Petrucci speaking. So there seems to be some degeneracy between the models. So you are able to explain same data with different values for the inner radius. But so in the near future, there will be a GRISM that should be launched. Can we expect to have answers from observations with this type of instrument? Or this is even hopeless because we will miss, I mean, there will be new stars to have the data above 10 keV, but we may be limited with GRISM too. So is there any simulations?
I'm not quite sure because I don't think this is necessarily a problem of, say, having low resolution. I think this is a problem of you can construct models in different ways to give you what you want. You can put so many components and then suddenly you fit a particular scenario that you have in mind. So I'm not so confident that having better data will do anything different than what we have now. Maybe, I don't know, maybe somebody else has a look into this.
How about multi-wavelength campaigns and multivariate comparison? So that's another topic, how to distinguish, maybe a possibility to distinguish between the alternative geometries. So if we just swiftly go to the second slide, which is the disk truncation and the disk jet corona connection. So we do have different interpretation of these two different geometries. For the Lampos corona to the left, so the connection to the jet here, and then on the right-hand side for the truncated disk and hot accretion flow. So in this, maybe in a couple of minutes, we have like a couple of questions raised, and one which I would like to raise is the low frequency QPOs and their optical infrared ultraviolet counterparts. So do we have both, in both of these geometries, do we have an explanation for those? there anyone in the Slack or chat? And so far, okay. Well, I mean, I think that could be an interesting point to consider when considering these two alternative geometries. So to try to connect, we know that there are low frequency quasi-periodic oscillations, which we see both in the X-rays and simultaneously in the optical, in the infrared. And it would be interesting to understand from these 2 points of view. So I can tell from the hot accretion flow truncated disk geometry how to produce them. So that's the hot disk, which would process, and then you would be able to simultaneously see its low frequency synchrotron emission in the optical infrared and then also X-rays. Then, of course, Matthew was suggesting that the jets would also process, maybe also could be considered these scenarios of what kind of specific properties and predictions you would expect. And that might be one possibility to distinguish.
I have a comment about type C QPOs, and something I found very interesting is the recent work with Insight HXMT data from Maxit 1820, which shows the type C QPOs detected at the same frequency all the way to very high energies, almost to 200 kVs. So is this consistent with the idea of an inner accretion precession flow? Will that still work?
If you have the one component basically which is producing you the optical and the high energy emission up to 200 or 300 kV, which we probably see in this Maxit J 1820 data, with the hybrid electrons in the integral data. So you would expect this also to have the QPOs. Okay, so we are a little bit over time already. I would like to thank all the speakers, all the people who have comments, and let's move on to the conference reception, right?